Hello everyone, and welcome to my talk about Airflow and how we adopted it in Bluevine and made it a critical part of our infrastructure, and how it helps us actually. My name is Noam Elfanbaum. A little bit about Bluevine. Bluevine is a fintech startup based in Tel Aviv and Redwood City, California. It provides working capital and banking services for SMBs in the US. And we use Python for almost everything, mostly backend code and ML. And of course, we're hiring. So if anyone is interested, feel free to reach out to me or to visit our virtual booth at the conference. We're also sponsors. About me, I lead the core engineering group at Bluevine. I live in Yesod Mala with my wife, kid, and dog. And I participated in organizing the first PyCon Israel. And I'm very happy to be here today as well. My talk is kind of a case study of how at Bluevine we use Airflow for actually all of our batch processing, and how we drifted away from Cronjobs. So the first part is migrating our machine learning workload to Airflow. The second part is how we needed to hack on Airflow in order to make it fit our custom needs and the problems we had while doing so. And the third one is how we're monitoring it in the day-to-day work. So part one, our migration to Airflow. So question is, what did we have before it? So like I said, we had cron jobs. We had many of them, as you can see in this diagram. Some of them were part of the same business process, but they didn't show it explicitly. You had to go into the code in order to see which task depend on which task, and they just ran on cron. So a task got up, saw on what user it needs to run on what population, it finished. Then another task came up, saw if all of its dependencies were met by looking at the database, and it started running on the user it found that are matching its needs, and so forth. This was pretty hectic to understand. So one of our goals was to more easily track and understand the dependencies between jobs. And also to track how users go through our flows, our business flows. What are the latencies? If they have any errors, it will be easier to debug in that way. One more requirement was to be able to run things faster, because running things on interval make it so that you lose time each time a task finishes and then waiting for the next task interval to start. We wanted the task to be triggered one after the other. We want to make it easier to scale. Scaling cron jobs is really, really difficult. You need to launch a new server, and then you need to migrate the jobs into the new server. It's not streamlined at all. And we want to have better control over our processes. For example, if we want to start a process, kill a process, you don't need to SSH into the server. You have some UI to do so. And Airflow fitted that bill perfectly. So a brief intro to Airflow. It's kind of a framework, you can say, like a framework that have different aspects. You can view the tasks that are in progress and see their statuses. You can trigger tasks, like I said before. By the way, this GIF is from their website. It shows what it does pretty nicely. So that's in the front end. On the back end, it's like a modular framework when you can decide on different tools to execute tasks. It gives you tools to, like I said, scale and so forth. So a DAG is a basic concept in Airflow. A DAG is a directed acyclic graph. What it actually means is just a tree with a direction that shows what task depends on the other. And Airflow uses it in order to demonstrate the whole flow that needs to happen in a single DAG. Behind the scene, Airflow had three core components. You have the scheduler, which calculates what needs to be run. You have the executor that actually executes the work. They can be based on Celery, Kubernetes, ACS, depends on your needs. And you have the web server, like we saw earlier. It's a UI and a way to control what's going on. The way we run Airflow at Bluevine is we have everything running on EC2, the scheduler, web server, and workers. We have Airflow needs a metadata database, and we use Postgres for it on top of RDS. We use Redis for our task queues, and Celery is the executor. Like I said before, you can choose different one. We use Celery on top of EC2. It's just running as a daemon and receiving jobs. Now we scale our workers manually because we don't really need to we don't have like drastic changes in our processing that we need to scale it up automatically, and it's pretty convenient to us. Another interesting thing in our setup is that we have isolated environment. As you can see here, we have an Airflow environment that has all of its dependencies. Then we have a Python environment that you use in order to run the actual process. So what happens is Airflow starts, it forks a Python shell in a virtual environment, and then it runs the application code. This is a little like cumbersome, but we get the benefit of not having to fix version conflicts, or when we just did the migration and we have a lot of package requirements for our environment, we didn't need to start understanding what is like how we need to change them in order for them to fit Airflow. Another thing is that now that we're upgrading packages, we're free to upgrade without dependency on Airflow. On the cons of doing this is that you're not fully integrated into the Airflow environment. So when, for example, you want to pass objects between two tasks, they won't pass as Python objects. You have to, like in our case, you have to output text. The bash process that runs the Python process needs to output text, and then you have to parse it, and it's a bit cumbersome to use, where if you would use Airflow in the same environment as your application, just have one single environment, you'll be able to just pass Python objects. But we're pretty happy with that virtual environment setup in the 2 years or more that we're using Airflow. Okay, so how we did the actual migration? We need to phase out the Cronjobs. In order to do so, we spun up an Airflow instance and Airflow setup, with all the requirements, and we started translating the cron job that we had into Airflow DAGs, and then we did the migration in small batches in the beginning. Took one cron job, moved it to Airflow so that it's stable. Once we felt more comfortable, we started moving in larger batches. I think we got up to 50 in a batch, and we had like 200 cron jobs. Okay, part 2 is so now we have all of our cron jobs in Airflow running, but they're not too clever, right? Because like we said, we just migrated the cron jobs as is into Airflow, and we're not utilizing the DAGs at all. So in part 2, we're going to describe how we started utilizing the DAG structure in order to create a fast onboarding flow. We call it like a streaming solution on top of Airflow. So in Bluevine, the user onboarding is, for example, we have different type of user onboarding, but this one is for getting credit from Bluevine, getting line of credit. So the users apply, and they're waiting online in order to get a result. We want to give them a result as fast as possible because it increases the chance that they'll take our offer. And we thought of using Airflow for that scenario because we're already familiar with it. All the logic and like the code that needs to run was already running in Airflow, and adopting a different solution, different real streaming solution would take us a while. So we just went for it. So this is a pretty good illustration of the onboarding flow. As you see, there are many tasks here that depends on one another. How did we implement that streaming design? So when a user signs up in the dashboard, in the user's UI, sorry, the wizard, it starts filling out details. As it fills details, we are making the Airflow start run on that user, on that specific user, not on batch of users, just on the one that signed up. In order to do that, we created events. When the user finished signing up for the first page, we have a few pages for the wizard. When the user finished signing up for the first one, we send an event, and then Airflow picked up that user and started running. The design was based on the concept of sensors that Airflow has. These are tasks that are checking some kind of event, and then they are checking an event. If it happened, they finish. If not, they're checking, like they're going to sleep and checking again in a certain interval. So let's see, here we have a better diagram that shows exactly how it works. So you can see the onboarding wizard, the user start, then it sends an event to Redis. We have a start sensor that is waiting for that event. So when that event arrives, we execute task A and B. Then we reach sensor C here. This is an illustration, of course. Then we reach sensor C. The user, while the user is applying, filling up info C page, sensor C is waiting. Once it finished info C, he's like the wizard sends an event that the user finished info C, and then task C can start running, processing the data that the user inputted. So, like I said earlier, we're progressing as the user progresses through the wizard. The idea is to save time and not start processing only when the user finishes the whole application. And then, once we deployed and start testing it, we hit a performance fall. We weren't so surprised by it, but it was a bit like alarming because we put all of our we put great effort into making Airflow be the solution. We didn't want to start working on a new one. So the Airflow, the performance wall that we hit was that Airflow scheduler took up to 30 seconds to compute the next task to run, which is quite a lot. Think about it. It's the time between like a task ends and a new task starts. It's unacceptable for it to be 30 seconds, right? So how we try to resolve it. Our first hack was to use a standalone trigger. Now that doesn't say much to you, so let me try to explain. The onboarding DAG, the way we built it is starting every few seconds and waiting for a new user to arrive. Now it uses the sensors in order to wait, like I showed you earlier. Now, when it starts, the DAG is creating all of its objects in the DB. For example, all of the tasks that needs to run, it put them on the DB. And on each scheduler cycle, the scheduler looks if any of those tasks can run. So if we have a DAG of 40 tasks and we have 20 DAGs running in parallel, then we have 800 tasks that the scheduler needs to find out if they need to run or not. And it's a shame to have those DAGs up if no users have arrived yet and we're just waiting for a new user to arrive. It becomes slow really quickly. So our solution was to have a triggering DAG that contains the sensor we saw earlier. So in this diagram, you can see it really well. When the triggering DAG is up, waiting for a new user to arrive. When the new user arrives, the sensors and like the user sends an event to the Redis. the start sensor sees that new event arrived, and then the next task is actually a task that triggers the big DAG that is running the full flow. And we're doing it so that the triggering DAG is sequential. It doesn't run a lot of DAGs in parallel. So when the scheduler is looking for that DAG, it doesn't need to calculate a lot of its task dependencies. There are only two, and there's only one up in each time. The onboarding DAG can have many runs in parallel, and that's okay though, because these are live users that are running. Okay, hack number 2 is to archive the DB tables. So, like we said, the Airflow is using the database in order to store all the metadata. So, on every run, the database fills up, and as the database grows larger and larger, it becomes slower and slower to query, right? Although it's indexed and everything. So in our setup, within 2 months, we already have 15 gig of data in the database, which is quite a lot. So our solution was to archive the DB table data and to keep only 2 weeks of history. We did so by moving the history into another table. And then in order to still have this data available, we created a view that combines the live table and the historical one. One gotcha with that solution is that if you remove the last run of the scheduler, the last run of the DAG from the live table into the archive table, then the scheduler will be confused and it will think it needs to run that specific DAG because it doesn't see any DAG in that table. That solution worked really well. It doesn't hurt performance at all, because you can still query and you don't hurt performance. So we were really happy with it. Hack number 3 is to create a dedicated fast airflow. This is really simple. You just take your workload that is time sensitive or latency sensitive and move it to a different airflow. So we had both what we called a streaming airflow and a batch jobs airflow. It produced really, really nice results. Reduction of 60% in average time spent on the step time, the time between execution of tasks. Our fourth hack was to patch the scheduler itself. Now this was quite a work. My colleague Amichai Horowitz worked on it a lot, and the way we approach it is to try to understand why the scheduler is so slow, because it doesn't really make sense for something to take 30 seconds, right? That's a lot of calculations in computer time. So Amichai started profiling the scheduler, and he saw that the scheduler is querying the database for each task to get its status. Like each task in a DAG, it's querying the database for it. So for example, if you have a DAG of 40 tasks and can have 20 parallel runs, it means you make 800 DB queries in order to understand what to run next. What Amichai did in order to resolve that is to make a single query for each DAG that gets the status of all of its tasks. So you might say it can be less accurate, but it doesn't really change so fast. And we patched it into, we sent it upstream to Airflow. It was accepted after a while. It took actually a few months for it to be accepted. And now it's part of Airflow 2.0. And in our test, it resulted in a reduction of 30% in the delay for the 90th percentile of users, which was pretty good, and we're happy we could contribute it back to the community. So in the end of the day, what we saw is that the time between tasks went back into 3 seconds instead of 30 seconds. It's still not the 2 seconds that was in the beginning, but that's okay. And the overall runtime for our use case for the onboarding flow took less than 3 minutes for 95% of the cases. So we are pretty happy with that results. You can see this diagram is the Gantt that Airflow shows you for how long does a certain DAG run. So we're not showing here the actual tasks that we're running, of course, but you can see that some of them are running in parallel, some of them are dependent on one another. It's a great view that Airflow provides. And one more thing, hack number 5, which isn't really a hack because it's like an official version, that Airflow 2.0 has improved its performance to a great extent, and it includes in the changes, of course, our patch. It also includes multiple schedulers. So you can run a few schedulers, not just one, and gain like scalability. Like you shouldn't have any performance issue with the scheduler when you have that option. It also includes better DAG serialization. It doesn't read all the DAGs from the file system each time it runs. It stores them in the DB and loads them when it needs to query. And another nice feature which is called fast follow, which means that a DAG that is linear, for example, like there is no multiple dependencies, there's one-to-one relationship, that the worker that took that task for execution will execute the next task immediately, not wait for the scheduler to schedule the next task for him, because he knows there isn't any other dependency for it. Now this table is something I took from the Airflow website. It's the difference between the performance between Airflow 2.0 and the previous versions, and you can see 7 times speed up. There's different use cases, but like you can see, it's pretty impressive. We're working on moving to Airflow 2.0 in all of our different Airflow setups. Actually, already some of them are already in production, and we see the results. Part 3, debug and monitoring. So, of course, every experienced, seasoned engineers know that you're not done until you can monitor and understand problem in production with your application. So in order to make it efficient and easy for us, we created plugins for Airflow. Airflow is like a modular platform. It actually uses Flask as a web server, and you can write your own web view for it. So the plugin that we wrote locates a certain user ID. You input a user ID, and then it returns the DAG graph and the DAG Gantt linked to them, so you can connect users with DAGs. This isn't something that like the regular Airflow users will need, because Airflow is more of a batch engine, and there is multiple DAGs. Actually, you can use it for also multiple users, but for us it was really critical in order to be able to debug production issues with specific users. For example, if you get something from support or anything like that. Okay, the next thing is we used Grafana in order to query the Airflow's DB. Like we said, all the data is there. You can get quite a lot of insights from it. So we can find the step time, like we showed you. This is Airflow step time, and how long Airflow takes to run. So you can see here the step time was around 2.6 seconds. And then we can monitor it to see if there are any issues, right? It's really, really useful. Another important facet here is that you need to, like, it's a good idea to use a DB replica and not the master replica, so your monitoring won't slow down the Airflow scheduler, which in versions prior to Airflow 2.0 is really slow. And another thing that needs to be mentioned is that now you can use the StatsD plugin, which is really nice. It's built into Airflow, and you can configure your own StatsD environment, and you can query. You can use Grafana in order to query. We transfer the StatsD metrics into Prometheus, and then you can query Prometheus, which is a time series database, and it's much more easier to query than querying the metadata Postgres instance that we have. So that's pretty nice. And the last thing I want to show you is the alerts we created. So also we want to know if there are problems with the flows before users feel it or before our internal employees feel it. So the first thing is we wanted to monitor the scheduler itself, right? Because if the scheduler doesn't work, nothing will be scheduled, especially where the scheduler is in Airflow version previous to 2.0 is a singular component, right? You can't run multiple scheduler at the same time. So in order to do so, we created another Grafana dashboard that queries a field in the database where the scheduler put its a heartbeat. It's like a timestamp with a heartbeat. And then you know the scheduler is up. And if it's not, we're getting an alert. You can see here the alerts. We're getting an alert that it's there's something wrong with it. And we reach the end of the conversation, the end of the talk. So I can say that for Bluevine, Airflow is really being a game changer if you compare it to a Cronjob setup. Since for all the reasons I showed you above, we also adapted it to other workloads than the machine learning one that I talked about, and it really became the only batch processing framework in Bluevine, and people love it. And that's it. That's our story. Hope you enjoyed it. Feel free to reach out with any questions. Bye bye.